My name is Nino, and this is my test 2. Chose problem 13, which is to use the repertoire method to find a closed form for the sum of -1 to the power of k times k squared from k equals 0 to n. So the first thing I'd like to discuss for this problem is the plan. So we were given a sum and asked to do the repertoire method on it. And typically the repertoire method is done on recursive functions. So the first thing we would like to do is convert our sum into a recursive function. The next thing to do is to come up with closed form functions, a of n, b of n, and so on, that cover the variables that are found in our recursive function. The next thing to do would be to set up an equation alpha a of n plus beta b of n, and so on, and by relating this to our recursive function, we will be able to find an alpha, beta, and so on that will that we could then put our closed form functions for a of n, b of n into that, and come up with a overall closed form function for our recursive function that we come up with. So to find a recursive function for our sum, we want to expand the terms of our sum. So we start with k equals 0. We get -1 to the power of 0 times 0 squared. Then we add k equals 1, which is -1 to the power of 1 times 1 squared. And we add all these terms up to k equals n, which is -1 to the power of n times n squared. And now each of these terms are the nth term of our recursive function s. So when k equals 0, we have s of 0. K equals n, we have s of n. So using these, we could come up with the function s of n is equal to -1 to the power of n times n squared plus s of n minus 1, where s of 0 equals 0. So the next thing to do would be find closed form functions whose recursive functions include the variable -1 to the power of n times n squared, because we want to get rid of that. Repertoire method, you want to express your recursive function that you want to find a closed form function in terms of smaller recursive functions that you already know the closed forms for. And then by plugging in these smaller recursive functions into an equation alpha a of times a of n plus beta times b of n plus so on, you can relate this to your original recursive function and solve for scalars alpha, beta, and so on that will transform these smaller recursive functions into your original recursive function. Now you could plug in the closed forms for a of n, b of n, and so on, and simplify it. And this will give you an overall closed form for the recursive function that you are searching for the closed form in. So if you have a recursive function that includes the term x squared, by making a of n x cubed, that's the closed form, the recursive form of x cubed includes the term x squared. So in this case, I try to use -1 to the power of n times n cubed in the hopes that the n cubed cancels out and leaves us with just the -1 to the power of n times n squared. And as you can see here, that doesn't work out. So we simply try a of n equals -1 to the power of n times n squared. And this gives us a recursive function a of n equals 2 times -1 to the power of n times n squared minus 2 times -1 to the power of n times n plus -1 to the power of n plus a of n minus 1. So our highest term here includes -1 to the power of n times n squared, which is good because this can be used to take out the -1 to the power of n times n squared in our original recursive function. This way we can solve for alpha, beta, and so on, which won't have variable terms like -1 to the power of n times n squared. We have our a of n. Now we try b of n equals -1 to the power of n times n. We solve for a recursive function, which is 2 times the -1 to the power of n times n minus -1 to the power of n plus b of n minus 1. And with these closed and recursive functions, we can now attempt the repertoire method. Come up with the function p of n equals alpha a of n plus beta b of n plus p of n minus 1. We can now plug in the recursive functions of a of n and b of n. So we plug these in and we simplify it. And then we group each of the terms for the coefficients for each of the variables. And now we set these equal to the coefficients for the variables of our original recursive function, which was just simply -1 to the power of n times n squared plus p of n minus 1, which means our -1 to the power of n times n and our -1 to the power of n, the coefficients for those are just 0. And now if we set 2 alpha equal to 1, we get alpha equals 1/2. And if we set -2 alpha plus 2 beta equal to 0, we get beta equals 1/2. And now that we have our alpha and beta, we can now plug in the closed form functions of a of n and b of n into our p of n using those alpha and beta values. And this should give us our closed form function. Now to plug in our alpha equals 1/2, beta equals 1/2, a of n equals -1 to the power of n times n squared, and b of n equals -1 to the power of n times n into our p of n equals alpha a of n plus beta b of n. And we simplified this out, and this gives us p of n equals -1 to the power of n times n squared plus n divided by 2, where p of 0 equals 0. Now, that should be our closed form function. And to test the values here and make sure that it's not offset by some constant k, we just plug in values, in this case 1 through 4, for our recursive function s of n and our closed form function p of n, and we can see our values match. But just a quick summary here, our sum k equals 0 to n of -1 to the power of k times k squared can be expressed as s of n equals -1 to the power of n times n squared plus s of n minus 1. Then using the functions a of n equals -1 to the power of n times n squared and b of n equals -1 to the power of n times n, as well as their recursive functions, we find that alpha and beta equals 1/2, and the function p of n equals alpha a of n plus beta b of n. And using all that information, we find that p of n equals -1 to the power of n times n squared plus n divided by 2. And that's it. That was my test 2 problem, and thank you for watching.